In this video, we'll consider integration involving natural logarithms. For the most part, we're looking at problems using substitution, but these integrals will involve the natural logarithm in one way or another. So we're going to start with some useful antiderivatives. We consider these as elementary antiderivatives because we know these antiderivatives based on derivative rules. So for example, we know that the integral of 1 over x dx is ln of the absolute value of x plus c. That's something we can verify because we can differentiate ln of absolute value of x plus c, and we get 1 over x. And we'll do that in a moment. The second useful antiderivative is the indefinite integral of ln of x dx, which is equal to x times ln of x minus x plus a constant. And we can verify these by differentiating the right-hand side and showing that we get the integrand. So for example, we can differentiate ln of absolute value of x plus c and get 1 over x, and we can differentiate x ln of x minus x plus c and get ln of x. Let's do that. Let's start with the first one. We want to differentiate ln of the absolute value of x, and we want to show that that's equal to 1 over x. Well, it's a little bit difficult to differentiate it when it has the absolute value sign in it. So we're going to break this apart into two cases. So case 1 is going to be where x is positive. Now in this case, ln of the absolute value of x is just ln of x. So if we differentiate ln of the absolute value of x, that's going to just be the same thing as the derivative with respect to x of ln of x. If we differentiate the plus c, of course, the derivative of a constant is 0. So we're just going to differentiate ln of absolute value of x. But if x is positive, absolute value of x is just x. And the derivative ln of x is equal to 1 over x, which is exactly what we claimed. Now let's look at case 2. So case 2, that's where x is negative. Now in this case, the absolute value of x is going to be the opposite of x. We know this because x is assumed to be negative. The absolute value of x must be positive, so it has to be the opposite sign to whatever x is. And that's why we write this way, the opposite of x. So in that case, we have that the derivative with respect to x of ln of the absolute value of x is going to be equal to the derivative with respect to x of ln of the absolute value of x, which is in this case negative x. Okay? In order to differentiate this, we need to use the chain rule. So we're going to differentiate ln of a thing. Well, if you differentiate ln of a thing, it's always 1 over whatever that thing is times the derivative of that thing, which in this case is negative x. Well, the derivative of negative x is negative 1. So you have negative 1 over x times negative 1, which of course is 1 over x. So once again, we find that the derivative of ln of absolute value of x, in this case when x is negative, is 1 over x. So either if x is positive or x is negative, you end up with 1 over x as the derivative. So what that means is the antiderivative of 1 over x dx is ln of the absolute value of x plus c. Now there's a subtlety here that we're only talking about intervals not containing 0. So either you're looking at an antiderivative of 1 over x where x is positive or where x is negative. But either way, you end up with the antiderivative of 1 over x dx being ln of the absolute value of x plus a constant. Okay, that's our first useful antiderivative. What about the second one? Again, we're going to do the same thing. We're going to just differentiate the term on the right. So we're going to differentiate with respect to x, x times ln of x minus x plus c. Let's write it in this time. Okay, so we're going to break this apart into the derivative with respect to x of x ln of x, it's supposed to be an n, minus the derivative with respect to x of x plus the derivative with respect to x of the constant c. Well, the derivative of this constant is going to be 0, so we don't need to worry about that. The first derivative here, the derivative of x ln of x, for that we're going to use the product rule. And for the second derivative, well, this is just the derivative of x with respect to x, so that's just going to be 1. So what are we going to have? This is going to be equal to the derivative with respect to x, and again, we're going to use the product rule, x ln of x on that, minus 1 plus 0. Well, we don't really need to write in the 0, so we won't anymore. All right, well, let's use the product rule on the first term. So it's the derivative of x times ln of x, so it's going to be the derivative with respect to x of the first term times the second plus the first, which is x, times the derivative of the second. So it's going to be the derivative of ln of x. ln of x. And then minus 1. Well, the derivative of x, that's going to be 1. And the derivative of ln of x, that's 1 over x. So what do we end up with? We end up with 1 times ln of x plus x times 1 over x minus 1. Well, 1 times ln of x, of course, that's just ln of x. And x divided by x, or x times 1 over x, that's 1. So we have here a 1 minus 1, that's just going to be 0, so our final answer is going to be ln of x plus 1 minus 1, which is ln of x. And therefore, we've established that the derivative of x ln of x minus x plus c is in fact ln of x. So what does that mean? The antiderivative of ln of x is x times ln of x minus x plus c, the constant of integration. Now let's go ahead and look at several examples. For our first example, example A, we're looking at the antiderivative ln of a times x. Now, because the argument of a natural logarithm needs to be positive, we should assume here that a is greater than 0. Okay, well, we're looking at the integral of ln of a thing. This is a composition. So usually when you have a composition, you want to start thinking about substitution. And in that case, your u is the inside function. Well, in this case, u is ax. So if u is a times x, then du is the derivative. So it's going to be a dx. Well, we don't have an a times dx, just a dx, but that's okay. You're allowed to multiply by a constant as long as you divide by that constant as well. So we're going to rewrite this as ln of a times x times, and I'm going to leave a little space here and write in the dx. What I want is I want to put in an a right there. But if I multiply by a, I have to divide by a as well. But that's okay. 1 over a times a is 1, so really we're just multiplying by 1, and that's allowed. All right, now if we do this, then what do we have? Well, this ln of ax becomes ln of u, and ax is du. So what do we have? We have 1 over a times the integral of ln of u du. Well, now we're looking at the antiderivative of ln of u with respect to u, and this is something that we know from our previous slide, from one of our useful antiderivatives. So this is going to give us 1 over a times, and the antiderivative of ln of u is going to be u ln of u minus u. And then, of course, we just tag on a plus c at the end. Now, all of these should be equalities, so let's put equal signs here. Okay, so we have 1 over a times, and what was u? U is equal to ax. So this is going to be ax times ln of ax minus ax. And then we have plus a c. Now, we can multiply this 1 over a through, we can distribute it, and what are we going to end up with? We're going to end up with, well, this 1 over a times ax ln of ax. Maybe we want to make that a bracket. And then minus 1 over a times ax. And then we have, of course, have the plus c at the end. And now, this 1 over a cancels without a, this 1 over a cancels with that a, and what do we end up with? We end up with x ln ax minus x plus a constant. Let's fix our c so it looks like that. Okay, and that's our answer. Now there actually is another way to do this, we can make use of the properties of the natural logarithm. And maybe just for this problem, I'll change the color of my pencil. So what I'm looking at now is an alternate solution. And this alternate solution will make use of the properties of the natural logarithm. In particular, we want to look at ln of ax, and logarithms turn products into addition. So this is ln of a plus ln of x, where ln of a is just a constant. Okay, so how does this work? The integral of ln of ax dx is then equal to the integral of the sum ln of a plus ln of x dx. And we can integrate each of these individually. So this is going to be the integral of ln of a. Now ln of a is just a constant, plus the integral of ln of x dx, which is something we know how to integrate from the previous slide. So this is going to be ln of a. It's a constant, so it's just going to be ln of a times x, plus, and now we know that this is x, ln of x minus x plus c. So what do we have? We have ln of ax plus x ln of x minus x plus c. Now these might not look immediately like the same thing, but we can take this ln of ax and that x times ln of x, and we can factor out the x term right there. So this is going to give us x times ln of a plus ln of x minus x plus c. And again, we use the properties of natural logarithms now to combine these. It's this rule right here. So this is just ln of a times x, and what do we end up with? We end up with x ln of a times x minus x plus a constant. And of course, this is the same thing that we had before. So this is an alternate way to do the same problem, and this is often the case with integration. You can find more than one way to find the correct answer. Let's look at example B. For this example, we want to integrate x over 1 plus x squared with respect to x. So what we're going to do is I'm going to rewrite this just a little bit. So I'm going to write this as the integral of 1 over 1 plus x squared times x dx. Okay. The reason I want to do this is that I'm looking at this 1 over 1 plus x squared, and this is a composition. I'm dividing by a function, so I want to use substitution where this is my composition and the inside function is the thing inside the denominator, so 1 plus x squared. So what I want to do is I want to let u be equal to 1 plus x squared, and then du is 2x dx. Now notice that we have not a 2x, but we have an x dx. We want a 2x dx. So once again, we're just going to multiply by a constant. So I'm going to multiply by 2. But if you multiply by 2, you have to divide by 2 as well. So we're going to have 1/2 there. Okay. Now if you do that, then this 1 over 1 plus x squared becomes 1 over u, and the 2x dx, that's du. So now what we have is the integral, so well, it's 1/2 times the integral of 1 over u du. And this we can integrate. This is equal to 1/2 times ln of the absolute value of u plus c, which is one of the useful antiderivatives we saw earlier. But now at this point we remind ourselves that u is equal to 1 plus x squared. So here we have a u, so I'm just going to replace that with 1 plus x squared. So this is going to be equal to 1/2 ln of the absolute value of 1 plus x squared, like so, plus a constant. All right? But 1 plus x squared is always positive. So let me just make this a little note here. 1 plus x squared is always positive. In fact, it's always bigger than 1. because x squared is a positive number, or possibly 0. It's certainly non-negative. So 1 plus x squared is always greater than or equal to 1. So in particular, it's greater than 0. It's always positive. Always positive. So what does that mean? That means that the absolute value of 1 plus x squared is the same thing as 1 plus x squared. So in other words, in this antiderivative here, we don't actually need the absolute value signs. So this is going to be equal to 1/2 ln of 1 plus x squared plus c. Now, it's not wrong if you include the absolute value signs, we just don't need them. And that's our answer. And we could, if we wanted to, confirm this by differentiating 1/2 times ln of 1 plus x squared, and we would find that, yes, indeed, using the chain rule, we get x over 1 plus x squared. For our next example, we're going to integrate tangent of x dx. Believe it or not, this is another substitution. It might not look like it the way we've written it now, but we're just going to rewrite tangent of x in a different way. So we're going to rewrite this as the integral of, well, tangent of x is sine x over cosine x. So let's write tangent x that way, sine x over cosine x dx. Now we can use it as a substitution. So what do I mean by that? I'm going to rewrite this as the integral of 1 over cosine of x times sine of x, like that. And now I'm going to look at this term, 1 over cosine of x. This is going to be my composition. The inside function is cosine of x, which is inside the denominator. So what I'm going to do is I'm going to let u be equal to cosine of x, like that, and then du is the derivative, which is the opposite of sine of x dx. Well, we have sine of x dx, but we actually need a minus sign in front. We need it to be the opposite. So what I'm going to do is I'm going to just put a minus sign in front, like that. Well, let's put some parentheses around it. But if I put a minus sign in front of the sign, I need to put another minus sign here. So the opposite of the opposite is going to be positive. So if I run a minus sign through the inside, I also have to run a minus sign through the outside. But this is okay, because now 1 over cosine of x becomes 1 over u, and the opposite of sine x dx, that's du, like so. So now we have the same kind of integral that we had before. It's the opposite of the integral of 1 over u du. And we know how to integrate this. This is our useful antiderivative that we saw earlier. So this is going to be the opposite of ln of the absolute value of u plus a constant. And now we remind ourselves that u is equal to cosine of x. So u is equal to cosine of x. There's a u. So we're just going to write this as the opposite of ln of the absolute value of cosine of x, like so, plus a constant. That's an absolute value sign there. Okay, and this indeed is the antiderivative of tangent of x, or the general antiderivative. Now, this isn't the only way that you might see this. It is sometimes written in another way. And to demonstrate that, let me just divide my sheet of paper into two parts here. And there's an alternate way to write this. So let me change the color of my pencil. So this is also written in another way. And what other way is it? Well, we're going to start with this term right here, minus ln of absolute value of cosine of x. So let's just rewrite it. But what I want to do is I want to rewrite it as minus 1, like that. Minus 1 times ln of the absolute value of cosine of x, like that. And let's just keep the plus c on here for fun. And now again, I'm going to use the properties of ln. So the property in question that I want to use, the fact that p times ln of, let's call it u, is equal to ln of u to the p, like that. That's the property I want to use, where in this case, u is my absolute value of cosine of x, and p is this minus 1. So I'm going to just use that property to rewrite this as ln of the absolute value of cosine of x, and then I'm going to write this to the -1 plus c. Now cosine to the -1 is 1 over cosine, so this is ln of, let's write this as 1 over cosine like this, like that, plus c, but 1 over cosine is also called secant, so we can write this as ln of the absolute value of secant of x plus a constant, like so. So these are absolute value signs here. This is secant right there, and this is parentheses there. Let me just fix my c there, so it looks like that. So this is another way that you'll often see the antiderivative of tangent written. You'll see it written as the natural logarithm of the absolute value of secant of x plus c. But these two right here, these two are the same. These are equal. So either one is acceptable. So that's our example C. Let's go ahead and do another example now. Example D. Here we want to integrate secant of x. Now we're going to use a similar trick that we used for tangent in the previous example, but this one is not exactly what you would call obvious or intuitive. I'm going to rewrite this expression in another way, but the way that I do it is not exactly obvious. So I'm going to rewrite this as the integral, that's supposed to be an integral symbol, of secant of x. Now I'm going to multiply it by something. Okay? Now I need to give myself a little bit of room here, so I'm going to just write it like that. Okay, so let's write it like that. And I'm going to write a fraction here, something divided by itself. Now the thing that I'm going to use is not exactly obvious, but I'm going to write something here, which is a fraction, which is something divided by itself. And the thing that I'm going to pick is secant x plus tangent x. I know that's the thing that you all had on the tip of your tongue, secant x plus tangent x. I'm going to put it in the top, and I'm also going to put it in the bottom. Secant x plus tangent x. Not exactly the most obvious thing to multiply and divide by. Now, first of all, let's just notice that I can do this because I'm multiplying and dividing by the same thing. So that's fine. But why did I pick this particular thing? Again, it's not obvious, it's not intuitive, but it does work. And the reason it works, if I multiply this secant of x by the numerator, it's going to give me the derivative of the denominator. Now again, that might not be apparent, so let's actually just work it out. So this is, I'm going to write this as the integral of, what I want to do is I want to multiply secant of x times the numerator. So we're going to have secant x times secant of x is secant x, and let me write it like this, quantity squared, plus secant x tangent x, like that. Okay, now that's the numerator, so we're integrating this, divided by secant x plus tangent x, like that, dx. Now my claim is that the derivative of the denominator is the numerator, and we can see that really because the derivative of tangent is secant squared, and the derivative of secant is tangent times secant. So let's just rewrite this. So we're going to rewrite it as the integral of, and it's going to be 1 over secant x plus tangent x. All of this is in the denominator, and I want 1 over that, times, and let's write this as secant x squared plus secant x tangent x, like so, dx. All right. Now my claim is that if I let u be secant of x plus tangent of x, then du is all of this right here. And we can check that. Let me just change the color here. So we're going to let u be equal to secant x plus tangent of x, and then du is the derivative. So the derivative of secant of x is going to be tangent x times secant x plus, and the derivative of tangent x is secant squared of x. So it's secant x quantity squared, and all of this is times dx. Let me just move this to the left a little bit so I can fit in the dx. So dx like that. And if you look, sure enough, that is the same as that. Okay, so what do we have? This term right here, all of that together is 1 over u, and all the rest of it is du. So that gives us the integral of 1 over u du, which of course is ln of the absolute value of u plus a constant. But what is u? U is all of this stuff, secant x plus tangent x. So we just plug that in right there. And we're going to end up with ln of secant x plus tangent x. And then, of course, plus a constant of integration. Like so. And there's our answer. So again, it's not entirely obvious or intuitive, but you can in fact check that if you differentiate the natural logarithm of secant x plus tangent x, that derivative is in fact secant of x. And the way that we show that is by using this rather unusual or perhaps unexpected substitution. We're multiplying by 1, but you just have to choose the right choice of 1. And again, it's not intuitive or obvious, but this choice does work. And you can see that if you multiply by secant of x plus tangent x divided by secant of x plus tangent of x, then the derivative of the denominator is in fact the numerator. And so then you can use the substitution that we use here. And we end up with the integral of 1 over u du, which is the natural logarithm of the absolute value of u plus c, which is exactly this. But of course, I need to include my absolute values. Absolute values. Don't want to forget those. For our next example, we're looking at the natural logarithm, or at least we're looking at the integral of the natural logarithm of the square root of x. Now, it might help if I just rewrite this as the integral of ln of x to the 1/2 dx. Because now I see that I have ln of x raised to a power. So once again, we want to use that rule that we were talking about earlier. Ln of x to a power is equal to p times ln of x. This is one of those useful properties of natural logarithms. If you have ln of x to a power, you can take the p down in front, and it becomes multiplication, p times ln of x. And we can do that here as well. So we're going to have the integral of 1/2 ln of x dx. And we can take that 1/2 outside. Now we have the integral of ln of x dx. And this is something that we know how to integrate, the integral of ln of x dx. That was one of our useful antiderivatives from earlier. So this is 1/2 times the antiderivative ln of x is going to be x ln of x minus x, and then we just throw on a plus c. And this is our antiderivative for the ln of the square root of x. Let's do another example. This one's a little bit more complicated. It's a little bit more subtle. We're looking at the integral of x cubed times ln of x dx. Now, actually, we're going to use the same rule that we used before. The rule that we want to use is ln of x to the p equals p times ln of x. Now, it's not immediately clear where we're going to use this, but it will come up. And actually, we're going to use it in reverse. So I'm going to take something that looks like p ln of x, and I'm going to rewrite it as ln x to the p. That's what we're going to do. So I'm going to start by taking our integral and rewriting it slightly. So I'm going to write this as the integral, that's supposed to be an integral symbol, of ln of x, and I'm going to write the x cubed over on the other side, like this. Okay. Now, ultimately, what I want is I want this x cubed to be my du. Now, that's not clear where that's going to come from, because if du is x cubed dx, then that means I need an x to the fourth somewhere. And where am I going to get an x to the fourth? It's actually going to come from right here, this ln of x. What I'm going to do is I'm going to multiply by 4 over 4, like that. I'm going to multiply by 4 over 4. Now, why on earth would I do that? So I'm going to take out the 1/4, and I'm going to have the integral of 4 ln of x times x cubed dx. And this is it right there. Because what I'm going to do is I'm going to use my properties of logarithms with p is equal to 4. So I'm going to let p be equal to 4. And then what does that tell me? That tells me that 4 times ln of x is equal to ln of x to the fourth. So what I'm going to do is I'm going to take this 4 and I'm going to bring it in right there. So it's going to end up right there. So let's actually do that. So we're going to have 1/4 integral ln of x to the fourth times x cubed dx. And now we have exactly what we need. We have an x to the fourth. So I'm going to let u be equal to x to the fourth, and then du is equal to 4x cubed dx. And we look at that and go, oh wait, that's just x cubed. We need a 4x cubed. But that's okay. It's just a constant. So you can multiply by the constant, and we'll do that. Let's use a different color. Let's go with green here. So we're going to multiply by 4. That's this 4 right here. We're going to multiply that 4 by that 4, but then we need to divide by 4. So that means we're going to multiply by another 1/4. So notice that we have two 1/4s out here. So that gives us 1/4 times 1/4 is 1 over 16 times the integral of ln of x to the fourth times 4x cubed dx. And we're letting u be equal to x to the 4. So that tells us that right here we have ln of u, and then this 4x cubed dx, that's our du. So what do we have now? We have 1 over 16 times the integral of ln of u du, and we know how to integrate that. The integral of ln of u du. So this is going to be 1 over 16 times, and it's u ln of u minus u plus a constant. Once again, this is one of the useful antiderivatives we saw at the beginning. But what is u? U is x to the fourth. So every place that we see a u here, we have to replace it with x to the fourth. So here's a u, there's a u, there's a u, and u is equal to x to the fourth. So we're going to end up with 1 over 16 times u, which is x to the fourth, times ln x to the fourth, minus u, which is x to the fourth, plus a constant. Plus a constant. And that's our answer right there. Okay. We have one more example that we're going to do. One more example, and here it is. Now this looks like quite a beast. The integral of 1 over x ln of x times ln of x. Notice here we have ln of x. So there's an ln of x inside another ln. And that's the key. There's an ln inside another ln. There's a composition there. Well, let's start by just rewriting this a little bit. So what I'm going to do is I'm going to write this one expression, this one fraction, as the product of several. So this is going to be the integral of 1 over, and I'm going to actually start with the composition of logarithms, ln of x. ln of x. So I have 1 over ln of x times 1 over ln of x times 1 over x, like that, dx. Okay? And the key idea is I have ln of another function. There's a composition there. And that composition is going to be key. But what am I going to let be equal to u? I'm actually going to let u be equal to this composition ln of x. Okay, that's what I'm going to do. So I'm going to let u be equal to, let me just fix my u. U is equal to ln of x. So what happens if I differentiate that to find du? Well, it's going to be the derivative. Well, it's ln of something. It's ln of something. So the derivative ln of something is 1 over that thing. But then you have to multiply by the derivative of that thing, which in this case is another ln of x dx. Well, what do we have here? We have the derivative of ln of x, that's 1 over x. So that tells us that du is equal to 1 over ln of x times 1 over x dx. And that should look kind of familiar because here it is right there. Right here. That's the same as that. 1 over ln of x times 1 over x dx. So all of this right here, this is our du. And here we have 1 over u. So as complicated as this expression started out as, it turns out that if you make this substitution, it's just the integral of 1 over u du, which is something we know how to integrate. That's ln of the absolute value, ln of the absolute value of u plus c. But again, what is u? U is ln of x. So this is going to be equal to ln of the absolute value of u, but that's ln of x plus c. Okay, let me just fix my handwriting a little bit. That's supposed to be a bracket, or a parenthesis rather. And this is supposed to be a constant of integration. Okay, these are absolute value signs. And there you have our answer. So this is our final answer right there.